Types of heat sinks and how they function in electronics. Heat sinks are crucial components used to dissipate heat generated by electronic devices such as CPUs, GPUs, power transistors, and LED lights. They come in various types, each designed for specific applications and cooling requirements. Here are some common types of heat sinks along with their functions. An aluminum heat sink is a type of heat sink made primarily from aluminum, a metal known for its excellent thermal conductivity and lightweight properties. Aluminum heat sinks are widely used in various electronic devices and systems to dissipate heat generated by components such as CPUs, GPUs, power transistors, and LED lights. Functionally, aluminum heat sinks serve to transfer heat away from electronic components to the surrounding environment, thereby preventing overheating and maintaining optimal operating temperatures. They work on the principle of conduction, where heat is transferred from the hot component to the heat sink and then dissipated into the surrounding air through convection and radiation. Aluminum heat sinks typically feature a design that maximizes surface area to enhance heat dissipation efficiency. This often involves the use of fins, ridges, or other geometric structures to increase the contact area with the air and promote better airflow. Additionally, aluminum's lightweight nature makes it easy to manufacture heat sinks with intricate designs and configurations tailored to specific cooling requirements. In summary, aluminum heat sinks play a crucial role in thermal management by effectively removing heat from electronic components, thus ensuring reliable performance and longevity of electronic devices and systems. A copper heat sink is a type of heat sink primarily made from copper, a metal renowned for its exceptional thermal conductivity. Copper heat sinks are utilized in various electronic devices and systems to dissipate heat generated by components such as CPUs, GPUs, power transistors, and high-power LEDs. Functionally, copper heat sinks serve the same purpose as other heat sinks, to transfer heat away from electronic components and dissipate it into the surrounding environment. However, copper's superior thermal conductivity compared to materials like aluminum allows for more efficient heat transfer and dissipation. Copper heat sinks typically feature a design optimized to maximize surface area, similar to aluminum heat sinks. This design may include fins, ridges, or other structures that increase the contact area with the air, promoting better airflow and heat dissipation. Additionally, copper's malleability allows for the creation of intricate heat sink designs tailored to specific cooling requirements. While copper heat sinks offer superior thermal conductivity, they are often heavier and more expensive than aluminum heat sinks. However, in applications where high thermal performance is critical, such as high-performance computing and industrial applications, the benefits of copper's excellent thermal conductivity may outweigh the drawbacks. In summary, copper heat sinks play a vital role in thermal management by efficiently transferring heat away from electronic components, ensuring reliable performance and longevity of electronic devices and systems, particularly in demanding environments. An active heat sink is a type of heat sink that incorporates additional components, such as fans or water pumps, to enhance the heat dissipation process. Unlike passive heat sinks, which rely solely on natural convection or thermal radiation, active heat sinks actively move air or liquid to improve cooling efficiency. Functionally, active heat sinks work by increasing airflow or liquid circulation around the heat-generating components, thereby enhancing heat transfer and dissipation. This active cooling mechanism allows for more effective thermal management, particularly in situations where passive cooling alone may not be sufficient to adequately control temperatures. Active heat sinks come in various configurations depending on the cooling requirements of the specific application. Fan-assisted heat sink. These heat sinks incorporate one or more fans to increase airflow over the heat sink fins, facilitating better heat dissipation. Fan-assisted heat sinks are commonly used in desktop computers, servers, and other electronics where airflow may be restricted or insufficient for passive cooling. Liquid-cooled heat sink. Liquid-cooled heat sinks use a circulating liquid, such as water or coolant, to absorb heat from the heat-generating components and carry it away to a radiator or heat exchanger. Liquid cooling offers higher thermal conductivity than air cooling and is often used in high-performance computing systems and overclock processors. Thermoelectric, Peltier, heat sink. Thermoelectric heat sinks utilize the Peltier effect to actively transfer heat away from electronic components. They consist of thermoelectric modules that create a temperature gradient when an electric current is applied, effectively moving heat from one side of the module to the other. Thermoelectric heat sinks are used in applications requiring precise temperature control or where traditional cooling methods are insufficient. The addition of active cooling components to heat sinks allows for more efficient thermal management, enabling electronic devices and systems to operate within safe temperature limits and maintain optimal performance. However, active heat sinks may be more complex, costly, and require additional power compared to passive heat sinks. A passive heat sink is a type of heat sink that relies solely on natural convection or thermal radiation to dissipate heat generated by electronic components. Unlike active heat sinks, which incorporate additional components such as fans or pumps to enhance cooling, passive heat sinks operate without any moving parts. Functionally, passive heat sinks work by transferring heat away from the heat-generating components to the surrounding air through conduction, and then allowing the air to carry the heat away through natural convection or thermal radiation. This process does not require any external power source and is driven solely by the temperature difference between the heat sink and the surrounding environment. Passive heat sinks come in various shapes and configurations, but they typically feature a design optimized to maximize surface area for better heat dissipation. This often involves the use of fins, ridges, or other geometric structures that increase the contact area with the air, promoting efficient heat transfer. Passive heat sinks are commonly used in a wide range of electronic devices and systems, including computers, laptops, LED lights, and power electronics. They are preferred in applications where noise, power consumption, or reliability concerns may limit the use of active cooling solutions. While passive heat sinks are generally simpler and quieter than active heat sinks, they may not be as effective in situations where high levels of heat dissipation are required. In such cases, active cooling solutions may be necessary to adequately control temperatures and prevent overheating of electronic components. A finned heatsink, also known simply as a finned heatsink, is a type of heatsink designed with extended fins or ridges to increase its surface area for better heat dissipation. The fins are typically made of thermally conductive materials such as aluminum or copper and are attached to a base plate that makes direct contact with the heat-generating component. Functionally, finned heat sinks work by transferring heat from the component to the fins, where it is then dissipated into the surrounding air through natural convection or thermal radiation. The increased surface area provided by the fins allows for more efficient heat transfer, enabling the heat sink to effectively cool the electronic device or system. Finned heat sinks come in various shapes and configurations depending on the specific cooling requirements of the application. Some common configurations include straight fin heat sink. Consists of straight fins attached perpendicular to the base plate. This simple design is effective for general-purpose cooling applications. Pin fin heat sink. Features cylindrical pins or posts instead of flat fins. Pin fin heat sinks offer higher surface area density and can be arranged in various configurations to optimize airflow and heat dissipation. Zigzag fin heat sink. Utilizes fins arranged in a zigzag pattern to increase surface area while maintaining structural integrity. This design is often used in compact electronic devices where space is limited. Swirl fin heat sink. Incorporates fins with a spiral or helical pattern to promote swirling airflow, which enhances heat transfer and dissipation efficiency. Finned heat sinks are commonly used in electronic devices and systems where passive cooling is sufficient to manage heat generated by components such as CPUs, GPUs, power transistors, and LED lights. They are versatile, cost-effective, and easy to install, making them a popular choice for thermal management in a wide range of applications. An extruded heat sink is a type of heat sink manufactured through the extrusion process, which involves pushing heated aluminum or copper through a die to create a specific shape. This process allows for the production of heat sinks with consistent cross-sectional profiles and complex geometries. Functionally, extruded heat sinks serve the same purpose as other types of heat sinks, to dissipate heat generated by electronic components and maintain optimal operating temperatures. However, the extrusion process offers several advantages in terms of design flexibility, cost-effectiveness, and manufacturing efficiency. Here's how the extrusion process works for producing heat sinks. Material selection. Aluminum is the most common material used for extruded heat sinks due to its excellent thermal conductivity, lightweight nature, and affordability. However, copper extruded heat sinks are also available for applications requiring higher thermal performance. Heating and extrusion. The selected material, usually in the form of rods or billets, is heated to a specific temperature to make it malleable. It is then forced through a shaped die using hydraulic pressure or a mechanical extrusion press. The die determines the cross-sectional profile and overall shape of the extruded heat sink. Cooling and finishing. As the material passes through the die, it undergoes rapid cooling, solidifying into the desired shape. After extrusion, the heat sink may undergo additional processes such as cutting, drilling, or surface treatment to meet specific requirements. Extruded heat sinks offer several benefits. Design flexibility. The extrusion process allows for the creation of heat sinks with intricate shapes, custom profiles, and integrated features such as fins or mounting holes. Cost-effectiveness. Extruded heat sinks are typically more cost-effective than other manufacturing methods, especially for large quantities or complex designs. Thermal performance. Aluminum extruded heat sinks provide good thermal conductivity, sufficient for many electronic cooling applications. Copper extruded heat sinks offer even higher thermal conductivity for demanding applications. Extruded heat sinks are commonly used in various electronic devices and systems, including computers, telecommunications equipment, LED lighting, power supplies, and automotive electronics. They are valued for their efficiency, versatility, and ability to meet diverse thermal management needs. A pin-fin heatsink is a type of heat sink characterized by a series of cylindrical pins or posts extending from a base plate. These pins increase the surface area available for heat transfer, enhancing the heat dissipation capability of the heatsink. Pin-fin heatsinks are commonly used in electronic devices and systems where efficient cooling is essential to maintain optimal operating temperatures. Functionally, pin-fin heatsinks work by transferring heat from the heat-generating component to the cylindrical pins, which then dissipate the heat into the surrounding air through convection. The increased surface area provided by the pins allows for more efficient heat transfer, enabling the heatsink to effectively cool the electronic device or system. Pin-fin heatsinks offer several advantages. High surface area density. The densely packed arrangement of cylindrical pins maximizes the surface area available for heat transfer, resulting in efficient cooling performance. Compact design. Pin-fin heatsinks can achieve high heat dissipation capabilities while occupying minimal space, making them suitable for compact electronic devices where space is limited. Versatility. Pin-fin heatsinks can be configured in various shapes and sizes to accommodate different cooling requirements and fit specific application needs. Uniform airflow. The cylindrical pins create channels that help guide airflow, promoting uniform distribution and efficient heat dissipation across the heatsink surface. Lightweight construction. Pin-fin heatsinks are typically made from lightweight materials such as aluminum, making them easy to handle and install. Overall, pin-fin heatsinks are a popular choice for thermal management in electronic devices and systems, including CPUs, GPUs, power transistors, LED lights, and other high-power components. Their efficient heat dissipation capability, compact design, and versatility make them well-suited for a wide range of cooling applications. A heat pipe heatsink is a specialized type of heatsink that utilizes heat pipes to enhance heat transfer and dissipation. Heat pipes are highly efficient heat transfer devices that operate on the principle of phase change, typically using a working fluid such as water, ammonia, or a refrigerant. Functionally, a heat pipe heatsink works by transferring heat from the heat-generating component to the evaporator section of the heat pipe. As the working fluid within the heat pipe absorbs heat, it undergoes a phase change from liquid to vapor. The vapor then travels along the length of the heat pipe to the condenser section, where it releases heat and condenses back into liquid. Finally, the condensed liquid returns to the evaporator section through capillary action or gravity, completing the heat transfer cycle. The use of heat pipes in heatsink design offers several advantages. High thermal conductivity. Heat pipes have exceptionally high thermal conductivity, allowing for efficient heat transfer over long distances with minimal thermal resistance. Uniform heat distribution. Heat pipes facilitate uniform heat distribution across the surface of the heatsink, ensuring effective cooling of the entire component. Directional flexibility. Heat pipes can be bent or shaped to accommodate different orientations and configurations, making them adaptable to various cooling requirements and space constraints. Passive operation. Heat pipe heat sinks operate passively, without the need for additional power sources or moving parts, resulting in silent and reliable cooling solutions. Heat pipe heat sinks are commonly used in electronic devices and systems where high-performance cooling is essential, such as high-end CPUs, GPUs, LED lights, and power electronics. They are particularly effective in applications with limited airflow or space constraints, as they can efficiently transfer heat over longer distances and across different orientations. Additionally, heat pipe heat sinks are often integrated with other cooling technologies, such as finned heat sinks or liquid cooling systems, to further enhance cooling performance. A liquid cooling heatsink, also known as a liquid-cooled heatsink or liquid cooling block, is a specialized cooling component used to dissipate heat generated by electronic devices. Unlike traditional air-cooled heatsinks, which rely on airflow for heat dissipation, liquid cooling heatsinks use a circulating liquid, such as water or coolant, to absorb and carry away heat from the heat-generating component. Functionally, a liquid cooling heatsink works by circulating a liquid coolant through a network of channels or tubes that make direct contact with the heat source. As the liquid passes through the channels, it absorbs heat from the component, increasing in temperature. The heated liquid then flows away from the component to a radiator or heat exchanger, where it releases heat into the surrounding environment and cools down. The cooled liquid is then recirculated back to the heatsink to repeat the cooling cycle. Liquid cooling heatsinks offer several advantages over air-cooled heatsinks. Higher thermal conductivity. Liquid coolant has higher thermal conductivity than air, allowing for more efficient heat transfer and dissipation. Uniform cooling. Liquid cooling provides more uniform cooling across the entire surface of the heat-generating component, reducing hot spots and thermal gradients. Silent operation. Liquid cooling systems operate quietly compared to air cooling solutions, making them ideal for noise-sensitive environments. Flexibility and scalability. Liquid cooling systems can be customized and scaled to accommodate varying cooling requirements, from small desktop computers to large data centers. Improved overclocking potential. Liquid cooling systems are capable of dissipating higher heat loads, allowing for more aggressive overclocking of CPUs and GPUs without risking overheating. Liquid cooling heatsinks are commonly used in high-performance computing systems, including gaming PCs, workstations, servers, and overclocked processors. They are also utilized in industrial applications where reliable and efficient cooling is essential for maintaining optimal performance and longevity of electronic components. While liquid cooling systems may require more upfront investment and maintenance compared to air cooling solutions, they offer superior thermal performance and are often preferred for demanding applications. A thermoelectric heatsink, also known as a Peltier cooler or thermoelectric cooler, TC, is a cooling device that utilizes the Peltier effect to actively transfer heat away from a heat source. Unlike traditional heat sinks that dissipate heat into the surrounding environment, thermoelectric heat sinks can both cool and heat components by manipulating the flow of electrical current through thermoelectric modules. Functionally, a thermoelectric heat sink works based on the Peltier effect, which occurs when an electric current passes through two different types of semiconductors joined together. When an electric current flows through the thermoelectric module, heat is absorbed at one junction, the cold side, and released at the other junction, the hot side. By reversing the direction of the electric current, the heat transfer process can be reversed, allowing the thermoelectric heatsink to both cool and heat as needed. Here's how a thermoelectric heatsink operates. Cooling mode. In cooling mode, an electric current is passed through the thermoelectric module, causing heat to be absorbed from the heat source at the cold side. This absorbed heat is then transferred to the hot side, where it is dissipated into the surrounding environment using a conventional heatsink or cooling fan. Heating mode. In heating mode, the direction of the electric current is reversed, causing heat to be absorbed from the surrounding environment at the cold side and released at the hot side. This allows the thermoelectric heatsink to provide heating as well as cooling capabilities. Thermoelectric heat sinks offer several advantages and applications. Precise temperature control. Thermoelectric heat sinks can achieve precise temperature control by adjusting the magnitude and direction of the electric current flowing through the thermoelectric modules. Compact design. Thermoelectric heat sinks are compact and lightweight compared to traditional cooling solutions, making them suitable for applications where space is limited. No moving parts. Thermoelectric heat sinks operate without any moving parts, resulting in silent operation and minimal maintenance requirements. Versatile applications. Thermoelectric heat sinks are used in a wide range of applications, including electronics cooling, automotive climate control, medical devices, and food and beverage cooling. While thermoelectric heat sinks offer precise temperature control and versatility, they are less efficient than traditional cooling methods in terms of energy consumption and heat transfer efficiency. Additionally, they may require additional power and generate waste heat, which must be managed effectively to prevent overheating. Despite these limitations, thermoelectric heat sinks remain a valuable cooling solution in applications where precise temperature control and compact design are paramount. Each type of heat sink has its advantages and is chosen based on factors such as the heat dissipation requirements, space limitations, and cost considerations of the specific application.